If systems continue becoming that powerful and that capable, we might not want them to be out there in the wild.
To make sense of the hardware that's powering the explosion in AI capabilities, I have on Leonard Heim today. He's a researcher at the Center for the Governance of AI, also the author of a fantastic AI compute syllabus primer, which I just spent the past few weeks obsessed and now feel like a smart person all of a sudden. Co-hosting with me today is Chris Miller, author of the recent FT Business Book of the Year, Chip Wars. Leonard, welcome to China Talk.
Thanks for having me.
So, what is compute?
I think basically, usually when I talk about compute, I mean something just around computing infrastructure, computing resources, right? And then it's like this vague thing where we're pointing to basically the thing which we as a civilization have been built over the last, what is it now, 100 years we've tried to. From processors to memory to more specialized stuff like GPUs in general, like those clunky things which are sometimes in your pocket, but also those things which fill up whole data warehouses, what we call data centers. So I think computing infrastructure is a good term to go for to describe compute.
So there's this concept of an AI triad, which I guess, can we say popularized by Ben Buchanan now on the NSC? The idea that data, algorithms, and compute are the three sort of inputs that you need in order to have a flourishing sort of product, as well as, one level of abstraction up, like national economic AI innovation system. Is it already baked in today, just the sort of like relationship of relative importance between those three?
Oh, yeah, I think the debate is not settled on this one yet. So I also like the term AI production function, where you're just basically asking yourself, well, we have AI systems which get created, and what are like the inputs into those systems? And then you have people who don't have a computer science background who try to simplify this. And as you just said, compute, algorithms, and data is like one way of going about it. And now the question is like, what is the most important of those? I guess it depends who you ask, right? I think one thing we can say over time, and of course we're focusing on compute. I'm claiming compute is pretty important and plays like a pretty important role. And somebody should be focusing on it, even if it's just a third of the production function, if we can say so. And in particular, if we look at like one subfield of AI, which is machine learning, compute plays like a really major role. And lastly, it's a necessary component, right? We cannot do AI stuff without processors, without compute. The question is like, how much do we need of it, right? Is your smartphone in your pocket sufficient, or do you actually need like a whole warehouse out of it? And the answer for machine learning is both. Depends on what you're doing.
Sure. So what are sort of like, what are the range? Can people even say today the sort of like range of futures in which actually you need giant server farms with, millions, if not billions of these chips? Or is there a world in which the sort of algorithms and data get so good that compute actually isn't really going to be a limiting factor on how good AI can get?
Yeah, I think it's important there to basically ask yourself the question, like, what are we doing? Where are we like in the AI lifecycle and the machine learning lifecycle? And what we can say is like when we train a system, right? When you like design like those neural network architectures and you show them a picture of a cat and you tell them this is a cat and the system tries to learn it. Given that we do this with like millions of examples, it's like really, really important. I think it's important when we think about like the compute requirements of AI systems to like look at the life cycle where we are with systems, right? So you have AI stuff running on your smartphone right now, be it Siri, be it Google Assistant, and like they're even trying to push it further that it completely runs on your smartphone and not on Google's or Apple's server for privacy-preserving reasons, right? The difference is there, those systems have been trained once, right? We showed them like dozens and millions hours of speech examples to be trained, and this usually gets done in data centers, and then we talk about warehouses of compute. But there is like a strong interest to actually deploy systems on your smartphone. We have this for voice assistants, but if you look at like newer systems, you mentioned ChatGPT. Well, this runs somewhere in Microsoft Azure in big data centers because it needs a lot of compute, even for inference. And it needs a lot of compute because I think they said something around 1 million users per day. So if you have 1 million users per day, you actually want to serve it to them. You have like quick latency, and then you run it on data centers. They also tend to be more efficient.
So what's the right way to think about productivity of the different aspects of the triad: compute, data, algorithms? I mean, we got the concept of Moore's law in terms of computing power. how would you measure productivity of algorithms or productivity of data changing over time?
Yeah, there's actually some pretty good research on this, right? So we once did a paper where we just basically looked at like all of the cutting edge ML systems and asked ourselves like how much compute, how much operations, how much flops, floating point operations do we need for training those systems, and try to plot this and like see what happened there. And what we saw that's like, oh, it doubled like every 6 months over the last 10 years. And that's like huge, right? Because if we compare this to Moore's law, it's only been doubling like every 2 years, like the original Moore's law. If we then try to find the same out with algorithmic efficiency or data, it gets way harder. We actually, so like, I'm also helping out with an organization which is called Epoch, where we actually also took a look at data trends, where we like try to investigate this, how much data is doubling. And the same for algorithmic efficiency. With data, it's like debatable. You have like lots of different dimensions, right? If you just think about like you have 10,000 pictures, if it's 10,000 pictures of the same cat, it's not like as useful as 10,000 pictures of a different cat from different angles or with different ratios, right? So there's like this quality angle, this quality spectrum to data. There's also like a bias spectrum to it, right? Depending on which data you feed it. I think it's like a discussion which we have a lot right now. The data sets on the internet are biased in certain ways, and so do the machine learning systems reproduce the same biases. One way how to think about algorithmic efficiency is just basically asking ourselves, do we get the same performance for less compute? Then we met algorithmic efficiency, right? And there's like also just a way of measuring it. There's like a blog post from OpenAI called AI and Efficiency. And my colleague Tamai, they just recently published a paper where they took a look at ImageNet and tried to figure this out. And they actually found out that just like the progress of algorithmic efficiency has been as important, roughly at least for image recognition, as in compute. Which is like kind of interesting, right? Because a bunch of people have always been saying like, well, it's only compute, it's only scaling all you need. But actually, while we scale those systems, we've also been making better algorithms which make more use out of the compute. And we also get more data sets. Like all of those things are scaling at the same time. But I think it's like really important to get like more research going to actually figure this out. I think there's like still lots to learn.
What are the inputs to more efficient algorithms? Obviously, you need smart people designing smart algorithms. But beyond that, if the inputs to more advanced semiconductors are better machine tools and better processes, how do you think about the inputs to better algorithms?
Yeah, I think naively you can just say talent. This is like naively the input. You just like need better people making better algorithms. The question is like how much you push them for it, right? I mean, there's like this thing in software engineering where people just like, there's like this term bloatware, where like our software just became more bloaty, less efficient over time because just processors became so good. There was like not really, you don't really need to, right? So like if your software is like not fast enough right now, you just wait 2 years and then it's gonna be fine, right? Because we have like nice Moore's law pushing across the edge. So I guess if Moore's laws and like computing progress, or like the computing price performance goes down, there might be more push towards like having more efficient systems, right? On the other side, we see it already right now. If you train systems and you spend like literally single to 2-digit millions on the training run for those systems, making a system's 10% more efficient, right? Like 10% less compute. That saves you a lot of money, right? And this is like in general, like in the interest of every business.
Well, it doesn't save you that much money though. I mean, what's interesting to me is like the sort of balance between open and closed in improving algorithms. You know, what you saw over, you know, OpenAI, they got a great team. They have like, you know, dozens of engineers, which is very different. And I'm sure there are some of the smartest folks out there, but it's very different than what you saw happen to Stable Diffusion when it was released, where, you know, you all of a sudden had the entire internet sort of working through sort of improvements to the model, and then all of a sudden, like, fast forward a few months and like you can run it on an iPhone, which is just something that I think there's like a real power in having this these sorts of algorithmic innovations be open sourced in a way where it'll be really interesting to see if the sort of you know, monetary edge of the OpenAIs and DeepMinds of the world not having necessarily to care about, you know, that spending $1 million or $2 more or less on their training run, as opposed to sort of like competing against whatever open source model, which may be a little more cash constrained, but will have far more sort of brains on the project trying to tweak what goes into the training and inference.
Yeah, That seems roughly right. I think it's like still important to differentiate that with just like the training of Stable Diffusion, right? Like to my understanding, I don't know how many people were like in the core team of staining Stable Diffusion. I guess it was not the whole world, and like I'm not even sure how much of this whole stack is like open source. I guess most of it, but if you actually would check like into GitHub and the commits, you might actually see like it's only a team of 10 people or something along these lines to actually deploy it. I think what we see in there, like once they released it, everybody wanted to run it locally on their computer, right? And this was like an exciting thing where like people actually pushing this. I think even just Apple just released something to make Stable Diffusion run locally on your MacBook M1 Airs. And that's like pretty exciting, right? Where they're just like trying to run this more efficient. But again, this is inference. This needs orders of magnitude less compute. You cannot train those systems on your laptop. You would probably wait until the heat death of the universe before this gets done.
So are we running out of compute, Leonard?
Yeah, tough question. Probably not. I think the question is more like, do we want to stop spending on compute? So what we've seen so far, I think I just mentioned it, if we look at training ML systems, how much compute we use to train ML systems, this has been doubling like every 6 months. Like according to an analysis, which is like from 2020, was doubling every 3 months. So leveled a bit off, right? Something doubling every 6 months. I think we also remember from COVID, exponential growth is like a pretty big deal and it cannot continue forever. And the reason why we could double every single time, because we had something like Moore's Law happening. And I like roughly describe Moore's Law as something just like the price performance doubles every 2 years, right? So we get more compute, more flops every 2 years. But if something only doubles every 2 years and the other thing doubles every 6 months, you can just basically only enable it with more spending. Right, and this is what we've seen. We're spending like way more money, like way more compute infrastructure to train those systems. And I think there was like a report by our folks from CSET, the Center for Security and Emerging Technology, where they're just trying to extrapolate this. And they had like some assumptions around like computing doesn't get better, and we can just see this can continue forever. At some point, we had like limits where like training a system costs $1 billion or like 1% of the US GDP. Are we willing to spend 1% on US GDP on training one model right now? I don't think so.
Yeah, but what if it's so sick? What if it's just the sickest model, Leonard?
Maybe we'll spend 1%. I like maybe 10%, then I was starting to become like a bit skeptical to actually do it. I think we need to see more progress.
I was facetious, but like, I mean, there is a world in which whatever this is turns into a Manhattan Project, and you end up needing sort of that level of tens of billions of dollars of government support that the private sector isn't going to get there. So maybe, Leonard, sort of like talk us through like the world in which that is the thing that nations need to do to compete.
Wait, and I would just add before that, $1 billion isn't that much for big tech firms. That's a totally viable amount of spending.
Yeah, maybe like $1 billion, like on the horizon, right? If you just like extrapolate this trend, like I once estimated the cost of Palm, which was like it's the biggest model to the current state, which is like a language model from Google, and like training this on their own cloud resources. If I would need to pay for it, right? Of course, they get it cheaper. It was like roughly 9 to 12 or 14 million, just like paying for this. And this is just training, right? This is just like one shot, you get it right. You still need to deploy it, which costs a lot of money. And you still need to play around with it and like develop it and like actually have like some hits and misses there, right? You're lucky if you get it done there. The world where we spend like $1 billion or like even more on those kinds of models, this is like a trend which I'm like deeply interested in. Just like I would like to learn more, just like how much are people like actually spending on those systems. There's just a problem. We have like some ways of actually estimating how much compute they use in the training run. I still don't have the insight, just like how much compute they need in total for the whole development, right? This is like still a question which I don't know like how much the computing resources they actually have. And my understanding right now is they're even competing internally for the computing resources because there's just a limited amount of chips, of AI chips, in the example of Google, of TPUs, on the example of OpenAI GPUs they have available. And there's like a competition, right? Does GPT-4 get like all of the GPUs, or is it maybe DALL-E 3? And those are like the open questions to me. And I expect before people start spending like billions or like 10 billions on a single training run on these models, I guess they want to make some money out of it. And this is what we need to see within the next couple of years. Maybe it's happening right now where we see like the commercialization of those big AI models and see if you can actually make money out of it.
I think I don't know. I don't see like, it's interesting because I saw a lot of charts in my reading, and there were a number of sort of studies that you linked to that sort of started to get into diminishing returns. when you increased, beyond the like 10, 15, $20 million threshold. But I mean, I think there's definitely a world in which whatever new algorithm can be 20x as good as the last one if you give it $1 billion worth of compute. And sort of like, I think now that the importance and sort of potential of these models has been generated, it would not be particularly difficult to convince VCs or a CEO of a public company or whatever that this is something that their firm needs to take a big bet on. I did think it was really funny that apparently Google like called some like board meeting the week, the emergency board meeting the week after GPT-3 was launched. I wouldn't be shocked if Sundar after that meeting was like, "Look, I got this. I'm just going to pour billions of dollars to blowing them out of the water."
Yeah, I think going back to this AI triad and the production function, what we still do not forget, it's not only compute, right? You cannot do AI models with only making them 10 million times bigger. You still need an algorithm. We have some algorithms. The neat thing we've been doing over years, like naively, we've just made models bigger. Turns out they're better. But we also needed is more data. And I think this is like also one question which we're facing there. Is like, if you want to scale up a model 100x, you also need like 50, 500x the amount of data. And this might actually also be a limitation because we cannot use any data, right? Do you want to train your model on Reddit? Probably not. I'm not sure how useful it is. Or like maybe only certain parts of the nice parts of Reddit or on Twitter or something. So there might actually be the case where you would like spend this little amount of money, but you don't have enough data to actually train those kinds of models. So you run into some kind of, you're running out of data literally. And I guess then it really depends on the domain. And if it's like language or image and those kinds of things.
Okay, so question again, kind of drilling into the economics of this. So you can spend more on designing smarter algorithms. You can spend more on compute, and then on the compute side, you can spend more sort of brute forcing and getting more transistors. But you can also spend on designing chips so that they're perfectly attuned to the algorithm that you're trying to run. So talk us through that dynamic. It gets more complex the more you dig into it in terms of the optimization cost if you're trying to think about this economically.
Right. Yeah. I think we now talked about like chips and compute, right? And I think the more interesting dynamic is that like what kind of chips are out there. And what I'm trying to draw here is something just like there's a spectrum around like chips which are like really general, they can do like lots of stuff, and chips which are really specialized. So if you think about general chips, this is a so-called CPU, a central processing unit, right? This is what you have in your smartphone. You can do lots of different things from scrolling Instagram to jumping on video calls like this. If you then move further across the spectrum, you have chips that are like kind of still general, but they're like for a certain task. And historically, we've seen something like a GPU, a graphics processing unit, which people came up with. Because what we're seeing basically when we calculating graphics, you do to the pixels the same thing all over again. So it's like, well, let's just build a chip which does like lots of stuff in parallel, right? And if you then move more further across the spectrum, we move to something what we call an ASIC, an application-specific integrated circuit. An ASIC is just like basically a chip designed for like a specific workload. It can only do one thing, but this thing like really, really well. Examples of this are your radio modem on your smartphone. It's like really, really well at like converting radio waves, like EM waves, into digital signals. Or another example of this is like Bitcoin. We had like lots of dedicated chips for Bitcoin. All they were doing, they were like this Bitcoin mining, which is like one specific hash function, and they're just recalculating over time. And if we move along the spectrum, right, the more specialized you get, the less general you are, right? But also the more efficient you get. And what we've seen with AI, basically, at some point people figured, well, we can use those GPUs because turns out training those AI algorithms is just like lots of metrics multiplication. So it's like sometimes people say it's embarrassingly parallel. And then they started using those GPUs and became way more efficient. And this is a good example where you basically were using chips which didn't have like more transistors or smaller transistors, maybe even like a bigger feature node, like even less transistors than your CPU. But turns out it's 10 to 100 times more efficient because you have a specialized architecture there. So we should not forget we have like this physical inspiration, right? We just have Moore's law, more transistors, more cores, all of those things. But actually we can also move across the spectrum just like where we have like architecture innovation, right? And this is what we've seen. And this is also partially what kicked off like the emergence of machine learning. Like many people say the deep learning area started with AlexNet, right? Deep learning, big networks means we need lots of compute. What they started doing there is starting to use those graphics processing units for this AI workloads, right? And lucky NVIDIA, they caught up on this, and now they basically have chips which are not used for gaming anymore. They're actually just dedicated AI chips used for training those big models, right? And this is like a way how you can basically innovate without putting more chips on the stuff, actually with architecture innovation. This is basically the algorithmic innovation on the compute level, right?
And so is it cheaper to or more efficient to innovate on the chip level or innovate in the algorithm level, or what's the right way to think about that trade-off?
Yeah, I think I cannot tell from the top of my head. I'm just like, it's like pretty hard. I mean, what we've seen on a chip level is just like ideas are getting harder to find, right? We need to spend exponential more money to get like smaller transistors. But it's like, it's turned out it's been pretty good. And like, turns out the companies who did it have become like really rich on it. What we've seen historically, we've done both at the same time. Ideally, I have an architecture innovation and the transistors get smaller. Then I have a double win, right? And this is to some degree also what NVIDIA has been doing. They continue using smaller nodes, right? While TSMC, SML, all the others continue innovating, which is great for them. At the same time, NVIDIA, who doesn't make the transistors smaller, they just come up with like new architectures which are more specialized towards like the workloads, in our case, machine learning training, to leverage this. And then you have like this multiplication effect, right? You've got a better architecture, you got better chips. And maybe one of this is going to like stop in the future, or it's just going to get harder to find. I guess like the same way how it's harder to make transistors smaller, it's harder to find like new architectural innovations, right? We've been now trying this for the last 10 years.
And on the data aspect, you mentioned the potential risk that we run out of relevant data, which, on the one hand, there's sort of an infinite amount of information in the world, but not all of it is in data form that you can easily plug in ones and zeros. But what's the right way to think about running out of data? It sort of seems like a implausible challenge to face, given that our main difficulty right now is making sense of all the data that exists in the world. So how would you characterize the challenge, and what's the first kind of limitation of data that we might actually end up bumping up against?
I think the first limitation is something like high quality data. Right? There's not an infinite amount of books out there in the world, unfortunately not. There's a limit to it. And like we feed surprisingly many into those systems, right? ChatGPT, GPT-3 has read many books, more than any of us combined could ever read within a lifetime. And there's just a limit to it. So basically what you want to have is like more data efficiency, right? Turns out I haven't read 10 million books, but sometimes I can maybe reason maybe as good as ChatGPT. Maybe, I don't know, I haven't played around with that much of it. But it's like there's like better data efficiency in humans, right? Compared to some other systems where we need to just feed in like lots of images, and it needs like to see a cat 10,000 times before it understands what a cat is. And I think we're doing a better job there. So like this idea of just like, high quality data being out there is like actually like a bottleneck, right? If I would only train kids on Reddit, maybe Reddit is not a good example, on 4chan, let's just say like something really terrible, wouldn't turn out that not surprisingly smart, actually turns out they would be pretty awful in reasoning and arguing and those kinds of things. Maybe Jordan can later link to this. We recently wrote a paper, I don't have the numbers from the top of my head, which is like asking first, are we going to be running out of data, where we try to make some estimates, just like how much data is out there, how much data do we actually produce, to get a handle on this. But this like looks in data in general. And I think what we're still lacking, there's like some good qualification of high quality data.
I don't know, Chris, as like an author and academic, how has it felt playing with this stuff over the past few weeks?
It's an interesting question. On the one hand, it's obviously kind of frightening because all of the things that I do, writing, it seems like are now replicable in some ways. On the other hand, it's sort of reassuring because although the results are really impressive, they're also really limited in obvious ways. And so I'm still not deeply fearful that I'm going to be replaced by a computer in the next decade or two. But maybe by 2040 or so, that moment will come. If so, I can welcome an early retirement, I guess. I don't know. That's the future we've all been hoping for, I guess.
You're not excited to use it as a research tool? I mean, like, I guess personally, it's just like I've had like some questions where Wikipedia didn't explain it well. And like, again, it's hard to know how much to trust it. Like, I really hope at some point they'll have like a confidence barometer or something alongside sort of like an ELO, like a win rate in like a football game or chess or something. But when we get that, like being able to like as a learning tool, this stuff is just going to be amazing.
So I think what's interesting though is that you said you know how to trust Wikipedia, which is also interesting because 10 years ago we would have said, well, Wikipedia is just articles populated by people like Jordan, totally untrustworthy, and yet now we all rely on it, and we have a pretty good sense of when it's real and when it's not trustworthy. So I think there's a learning aspect on our end that we're going to need to get comfortable with, and we will over time.
Yeah. Or just your students, handing in essays they didn't write themselves. So maybe that's the thing you're going to be facing next.
Are you going to do all oral exams? I think that's the only answer.
And not via Zoom too, because those will be fakeable soon as well.
Yeah. I mean, I think like once it can figure out, because citations, that's what it's like you can't write a paper. It can't write a paper that can like trace knowledge back to the source yet. But it will soon. And it's going to be, just what's going to happen to education is going to be a really interesting thing. And again, I think there's like just so much upside here of, giving better, sort of more tailored instruction. But, the evaluation methods that have worked for the past, I don't know, few thousand years are just not going to be functional anymore because.
But I think it's good because we'll have to specialize on what we ought to specialize in, which is creative thinking, rather than rote processes that we can train machines to do. So I have a question about kind of thinking about machines. We have phrases like machine learning. So I guess the concept of machines is built in there. But it seems to me that we haven't really come to terms with the extent to which data centers are in fact the factories of the future, and all of the sort of, and they're the machine tools of the 21st century, I guess, if you will. They're going to do all of the work in producing new products for us. And so how would you think about sort of the economic impact of not sort of the dollar and cents fashion, but so the work data centers will be doing in terms of the economy over the next half century, and the role that they'll play? I guess I'm thinking like if River Rouge and Henry Ford was the kind of the key production site of the 20th century, our data centers the key production site of the 21st century, and how do we get our heads around that?
Yeah, I think that's like the angle to think about AI as like a general purpose technology, right? And if we think about a general purpose technology, we have a couple of those. Electricity, the steam engine are some of them, and they're just like, can we imagine a world without them? Well, not anymore, right? And I think we might face the same with AI, and as an underlying resource for AI, we face the same with compute. So compute might just become some kind of commodity, or just like first like a critical infrastructure. Maybe a state will start thinking about its data centers the same way it thinks about its water treatment facilities, right? I think those are like actually the ways how to think about it. And then just like, I once said something just like, maybe the next big inequality will be access to compute. Because like the access to compute means the access to AI systems. We just talked about it. Turns out they're like immensely helpful. And whoever has the most access to them has like, the lead on whatever, be it economically or in other domains, even science domains. So seems really important to think about compute.
So I like the analogy of infrastructure, but then I think, is a data center really like water treatment? And it seems like there's a fair amount of simplicity in water treatment that we don't have in data centers. And so I guess that's part of the story, the infrastructure part. But it's not just water treatment, because it's not just the power going into the old factory. It's also the machine tools themselves, and the hammering out of new equipment is sort of what our semiconductors and servers are doing in data centers as well.
It's like a globally fungible good. It's also something that is on this like exponentially growing, well, depends how exponential, but like it's something where, I don't know what the like productivity increase of like electricity or water has been over the past few centuries. I think like data centers are like, of course, way more complex than just like water treatment facilities, right? I mean, like, Chris, you're the expert on this, right? Just think about the whole geopolitics of this whole thing. And there's like another way how to think about it. So there's like an OECD expert group, which is called OECD Expert Group on AI, Compute, and Climate, which I'm part of. And there's like some slogan which we usually say, there's like a compute divide within countries, but there's also a compute divide between countries, right? If we just think AI is going to be a powerful technology and compute is just like really important input to the AI technology, this compute divide has like huge implications. And the best way how we currently see this playing out is the AI research field is like somewhat of a weird research field because we see industry labs leading there.
This is historically not the case in a bunch of stuff, right? They didn't lead particle research or like fundamental physics research, but with machine learning research, turns out most of our powerful models are coming from OpenAI, DeepMind, Google, big tech, all of those organizations. And actually, this is what this compute divide refers to. If you look at the most powerful systems, none, like little of them are coming out of academia, and it just gets worse every single day. And part of the reason, part of the explanation is probably this compute divide, right? Just like having access to those critical resources plays a really important role, right? It's to the same degree where you have like some factories, they didn't have access to electricity. Well, it turns out they're just like 100 times less productive then.
So, Leonard, what are the arguments for and against spending federal money to give university researchers and, I don't know, startups more, or less well-funded startups, more access to this compute?
Yeah, I think you're pointing to something which is like a big discussion in the US right now, which is called the NARE, the National AI Research Resource, right? The NARE has been called because like one of the motivations, what I just described, we have like this compute divide. And what the NARE tries to do is just like try to give academics and maybe also startups or like other small businesses access to compute. Yeah, what are the arguments in favor of it? I think I just described it, right? To like participate at the frontier of machine learning research. If you think about creating systems, you need a lot of compute. Now it's already debatable, is this the frontier of ML research? There's like a reason why Google and all the others create systems, because systems are the things which you eventually make money out of, right? Academic incentives might be different. They just might actually play around, just like understanding how those systems actually work, how are they reasoning, all those kinds of things. But on the other side, you might want to play around with those cutting edge systems to see how they actually work. So like for them to participate at the frontier of AI research, they need access to compute. The problem is already just like, how do we give them access to compute? I think it would just be wrong to just like, here's a big compute cluster, do whatever you do. There is another difference compared to academia and like a single PhD student compared to OpenAI and Google. It's just like how the way they work, right? PhD students are often like this, the single person trying to do their project. And if they're not trying to train like a GPT-3 size models, they will face like lots of challenges, because turns out you need to know lots of different disciplines to train those systems, right? It's become a big science to some degree. So you need your infrastructure engineer who helps you to deploy the model. Well, then you need this other person who constantly checks this training run if things are going well and if your GPUs are failing. And then maybe you need another engineer who like actually deploys it efficiently and like can take it apart. So if like actually it's like more of a team effort. So this already just giving them compute might not actually solve the problem. There's like way more to it. And then also the question like, how do you give them compute? Do you want to set up like another high performance cluster next to the university? Do you want to just give them money and they buy it from AWS, they buy it from Amazon Web Service, or they might buy it from Microsoft Azure? Or does just everybody get like another computer under the desk? I think those are like the questions we still need to figure out, like what is the best way of actually giving them access to this compute so they actually are using it. And I think only compute is not the answer. There's like a bit more to it. There's like a whole engineering aspect to like deploying and running and training those big models for actually going about it. This might like be like a bit not argument against it, but almost like, well, actually we haven't figured out completely yet.
I mean, I think the answer is you give them AWS credits, right? Like whatever federal version of AWS is going to be like bad, and giving everyone an A100 under their desk doesn't solve the problem. So, right? Am I missing something?
Maybe. I mean, I'm just like, if you like, I mean, like, I kind of agree. Just like, there's like this big worry for many people. It's like, oh gosh, a federal project. Like, we have high performance clusters, right? And there's a reason why people sometimes like to go to AWS and Microsoft Azure, because they just work well. It's well documented. You pay what you get for. They're just efficient. And we don't always have efficient systems within governmental systems, right? When a DOE runs something. On the other side, as I just said, like, if I just give you now the credits to train a system, you know, it's pretty hard. You need to get you just need to know run those systems, and it's become its own science to deploy those large training runs, because it's not, as you just said, it's not a single A100 under your desk you're running this on. We're talking about thousands of chips you're doing it. This is distributed computing. This is its own academic discipline to make this efficient. Again, if you don't make it not efficient, if you're just like, I don't care about optimization, you're like 10 times worse than you could be, which means you spend 10 times more money, which means you spend 10 million instead of 1 million. I guess your PI is not going to be that excited about it, right? So there's just like still this aspect where you probably need operational support for deploying those models. I think this is probably the thing which I would be excited about, to just like not only give them the compute, you actually need to train them how to use it and help them along the way. Because this is the edge which OpenAI, DeepMind, and all the others have. Those are teams. teams with different disciplines, and everybody does their part of the whole machine learning stack you eventually need to learn.
Yes. So what are the counter arguments to providing this type of service?
Yeah, let's just assume they're successful, right? If we give them enough compute, we're going to be creating powerful AI systems. There is like this worry I was just talked about. Those systems get ever more powerful, right? And I think there's like an interesting discussion which started a couple of months ago. It's around the open sourcing of those systems, right? Stable Diffusion made like a lot of noise asking for the democratization of just like AI models. And I do think it's like actually a complex matter. Like I'm coming from an engineering discipline. I've been a huge fan of open source my whole lifetime. And now I'm like advocating a bit against it. Where I'm just like, those systems in the future will be ever more powerful, ever more capable. And we should really think carefully about deploying them into the real world because they can do real harm via misuse. And this is basically what we need to consider with the NAIR, which is like, if academics are training those systems, current incentive systems are aligned this way that you just want to migrate the best new powerful systems because you get like the new benchmark, and this probably gets you like a new NeurIPS publication. And they might just put it out there. And then what might happen, you have like a new, really strong language model. Somebody might just misuse it for propaganda and other stuff. And it turns out that actually training the system is part of the hard thing, right? The reason I don't have my own GPT-3 is because I'm not smart enough and I don't have enough money, right? But if somebody would just not put it out there, the smartness required to actually deploy the systems like significantly less. And guess what? The money required to deploy them is also significantly less. And that's part of the reason why my colleague Marcus and me has been recently advocating to the NAIR, just like, maybe you should consider something what we call structured access. Instead of open sourcing those models, give a way for people to access those systems, to use those systems, but like in a safe and secure way. And an example of this would be via, for example, an API where researchers can interface with this, but the model is not out there in the wild and everybody can just deploy it on the systems. And I think this is like exactly the thing which we need to look out for, just like the misuse of future ML systems. I'm not saying it's like a big danger right now, but I think we're getting some early hints at this with Stable Diffusion where it might be misused, right? But in the future, we should even consider it more if systems continue becoming, that powerful and that capable. We might not actually want them. Again, as a society, as a democratic process, we might not want them to be out there in the wild.
Well, I guess that brings up the question of governance, of who decides and how those decisions are made. Is that a corporate decision? Are there new institutions set up? Is that governments deciding?
Yeah, and I think this is exactly the discussion which NAIR should be having. I think what not the answer is that the researcher who trained the model should decide. Actually, you might be arguing this is anti-democratic, right? Because it's not the population to decide, right? So like actually having like a process, how we best go about it and how we basically balance the benefits and the downsides of those models, right? And like structured access is like one way how you might want to go about it, which brings you the benefits, but tries to minimize the downside risks. And I think this is just like a really important thing to look out. Yeah, if those systems become like stronger and stronger over time.
Yeah. And this sort of brings us, this is my new game, is see how long I can do a show without bringing out China. We've made it to 36 minutes. So this is the, this is where we get into this sort of competitive dynamics, right? Because I'm sure there will be researchers out there making the argument that, look, the more you try to shape, like, look, this is the new fire. The more you try to sort of shape and contain and, have controls and like be careful or whatever, the easier it is for researchers who don't face those constraints to progress ahead. And particularly when you have this sort of like open-close dynamic where a more open system will have it, where sort of a more open system will allow more people to sort of work on, iterate, progress it, both on the, maybe harder to do it on the training side, but certainly on the inference side, you could see a universe in which this sort of thing allows nations or researchers inside of nations who are less stressed out about these sorts of things to make up time and capability. What generally is the right way to think about which parts of the triad are easiest and hardest to diffuse?
Yeah. I think that's like a strong argument. Like, again, like the triad, right? We have like algorithms, we have data, and we have compute. Let's just like try to work for them. If we look at data, is There's like actually open source data sets. So for example, if you look at the data set, which was trained on Stable Diffusion, it's an open source data set. You guys could be using it right now. And anybody else in whatever country you want to name now. If we look at algorithms, sometimes the same, right? And there's like a spectrum how you can publicize algorithms. You can just like not talk about them. You can write up a paper where you like kind of describe it, but the code is not open source. And the most extreme example is like, yep, the code is open source. Here it is. This is the case for like lots of stuff in machine learning with all of the good benefits, right? All the benefits that TensorFlow, PyTorch, like those basic fundamental building blocks of machine learning systems are out there and open source and that you can use them. What those two things have in common, they're digital, right? So if I would now hack into your computer and you have a secret data set, I press Commando C, Commando V, here we go, I have it. Can you stop me from doing it? It's gonna be pretty hard, right? Because it's just like, I just created a copy. So it's not a rivalrous good, actually, right? People can use it at the same time, multiplanar. The same goes for algorithms, the same goes for data. That's a big exception for compute. If you're running an algorithm on your computer right now, I cannot use it. It's just like fundamental physical limits. There's a limit on how much algorithms can be run right now in the world, given on the amount of compute out there. So this makes compute actually like an interesting node because you can just not simply hack it and steal it. There's like some ways how you can technically hack a data center and you can run and train your system there. But what you should notice, because it turns out that actually drawing energy, your GPUs are at full utilization and you cannot run your system, right? So I think it's like a neat way of like thinking about the diffusion. It's like, what is getting diffused anyways? This basically depends on the publication norms of researchers. And also, if you just think about like people hacking and stealing those kinds of algorithms, it's like really hard to prevent the hacking from data and algorithms. In particular, you know, like cybersecurity turns out is a mess. Turns out usually you can hack into companies, even to the best secured ones. Seems really hard. I'm pretty excited about compute as the resource, which is like you cannot digital steal. It's like it's a physical thing, right? And then not to forget, next to like those fundamental compute properties, all of the properties of the supply chain, of the state of affairs, how everything is built up right now.
But you can still steal physical things. It's just a little bit harder. We've talked a lot on China Talk about export controls, and of course, one of the sort of like flagship pieces of the Biden administration's export control regime is this restriction of the highest performance compute being able to be imported into China. So, I think we've sort of covered pretty in depth on this show the challenges that China will have to sort of domesticate the manufacture of those chips. However, there are millions of H100s sold every year, and diverting some of that supply down into some Guizhou server farm isn't the hardest thing in the world to do. So I guess the question then, Leonard, is like, can you like contraband your way into having enough compute to do things which aren't just the national security implication stuff of, having 1,000 or 2,000 GPUs to model a nuclear weapon or whatever. But, if we end up on a technological timeline where you need to run $500 million, billion-dollar training runs, can kind of gaining access to that compute in a sneaky way be a potential solution for China?
Yeah, that's a good question. So turns out you need a lot of chips for this, right? So it's not about just like, I think there was recently a news where somebody tried to smuggle some chips into China with a fake baby bump. And they had like, I don't know, like 30 or 40 like Intel CPUs in there and some iPhones.
But that story was misreported. That is like a...
Was it misreported?
It was.
What's wrong about it?
Well, because the Chinese government caught them. That was someone trying to evade import taxes. That's very different than a state-run, effort to like obtain strategic compute.
Yeah, I agree. I think indeed, just like the Chinese government reported this, right? I'm just like saying like an example, just like there's a limit to how many you can put in your baby bump. Like assuming they would just go through, I don't know, the airport in San Francisco, the TSA there would just be like, okay, there's like a limit to how many A100s you can put in your backpack, right?
But is there? I don't know. Like, look, a lot of cocaine comes in and out of every country in the world. Like you can figure this out, especially if you're a nation state. I mean,
But so I think that's the wrong, I think, way to think about it.
okay,
Because a thousand chips does not a data center make, nor does 10,000. There's a lot more that has to happen than just getting chips into a country. And I think the interesting part of this is that data centers are big buildings you can see from space, and the numbers that we're talking about are actually quite small. And so it's a much more knowable question as to where are chips ending up, or what chips are ending up in a given building, than tracking cocaine flows into the United States, because the cocaine ends up in a million different consumers, whereas the chips end up in I don't know 100 different data centers.
but
Yeah.
it can go from narrow to wide to narrow, right? So you can have Intel selling it
Yeah.
to 100 distributors, which then goes to 10,000 or 100,000 places. And even if it ends up in one place, it's like, okay, I guess like the Air Force can bomb it in a war, but if America wants to turn the lights out at these places, they can. Like it's like an Iranian centrifuge place, but I don't know if that necessarily solves the issue here, Chris.
Well, I think in terms of understanding how things are entering China, let's say, and the networks that are delivering them, the fact that you've got a limited number of end customers makes the tracking problem a lot more durable, because you can. Yeah, go ahead.
Just in general, just like so, maybe the big difference compared to cocaine is just like you guys heard about the semiconductor supply chain. Turns out it's really concentrated and really complex, right? If I would be desiring to build cocaine, probably not here in Switzerland, but somewhere else, I could probably get it done, right? But actually, building A100s, I don't know, man. Even at the end of my lifetime, I don't get it done, right? I mean, you chatted a lot about just building a sovereign industry. So what we eventually see, if you look at all NVIDIA GPUs, or even all NVIDIA A100s, Google TPUs or something, they're coming out of replication university, they're coming out of TSMC, right? So maybe there's just some way how you use normal supply chain tracking methods, so just making sure where they end up. And there's way less actors. The market is really concentrated, which we should actually look at. So I think the general norm is just something it's hard to enforce this, and we need to learn more how to actually enforce it and make those things successful, right? And diverging 10 million chips is different than diverging 5,000 chips, but maybe the 5,000 to 10,000 chips are sufficient to training those systems, and this is how you initially get started. I think the more interesting dynamic here is just compute is not the thing. We're using compute right now, right? This call is running on some computer. I don't know where it is, but it's not at our home, right? But it's also running on a server. So actually, you can be, let's just say, China and train a model on compute, which is sitting in Arizona via cloud computing, right? This is what we historically have seen. And I think this is also opening up this really interesting question. It's okay, cool. The chips do stop going to China, but how would we actually make sure they stop using those cutting edge systems, right? How can we make sure that in the future they're not going to be using AWS, Microsoft Azure Compute? I think this opens up a new complete domain of, how do you want to export control as cloud computing, right? Export cloud computing from the US. And this is an open question to me, how we're actually going to be going about this, the whole cloud computing thing, and making sure this compute does not get misused. Because clearly, what are you going to be doing? Why is the reason if I don't have A100s at home, I use cloud computing because I don't have them at home. So why isn't not the Chinese government going to be doing the same in the future?
Well, there's an interesting Chinese government policy decision as well as to what extent do you allow or not allow the transfer of relevant data abroad to do that.
And I think what we historically have seen is just they mostly use their own data centers, right, for data privacy reasons. And they will continue doing so because at the moment they still have their A100s. But if we look 5 years into the future and they don't have the newest NVIDIA chips, the H100, there might be some desire to actually use our cloud computing technology. If Moore's laws continue, if the price performance continues to double every 2 years, there is a strong desire to use new computing technologies and then actually just accessing them via cloud computing legally. Or maybe you start setting up some offshore entities which are registered wherever, and then they're just right? And there's lots of things we should then look at, just who's actually the customer of AWS, right? Maybe they just want to implement a really strong know your customer scheme. And I think already right now they would not be allowed to give cloud computing to companies on the entity list, right? This is they're already forbidden there. How do they enforce it? I actually don't know. But I guess they need to by law, right?
Well, and there are also, I think, we can fact check this maybe. I believe there are Alibaba cloud facilities outside of China, which can legally, I think, and I believe they can legally buy control GPUs because they're outside of China?
Yeah, I would be curious what the answers are and just like how we go about it. And it seems like an interesting field to assuming you're in favor of these export restrictions, which is debatable. Those are the things you want to be looking at next.
Yeah, 2 points. So first, I mean, the export controls explicitly do not prevent Chinese firms that aren't, tied to the military-industrial complex in a tight way to using server farms in Singapore. Again, that would be a very tricky secondary sanction to enforce, but it's still totally fine right now. The other point, which I think is really interesting, is we've seen in the past few months NVIDIA and Jensen Huang basically saying, look, our latest chip, like we retooled it and it's like 97% as good, and we're gonna still sell it into China and we're not gonna lose a lot of sales. But like exactly as you said, Leonard, like that's not gonna cut it 5 years from now when the latest tech you can't squeeze under the export regulations that were put up in 2022 in a way that will end up satisfying customers and create sort of like globally competitive products. So if and when that happens, that's really when the rubber is gonna hit the road on this. And as Chinese firms more and more are gonna be pushed out into wanting to get their compute from outside of China for the latest, greatest, most efficient, sort of cheapest to run technology.
Indeed. I think that's also just like this whole new notion where we just basically think about more compute means more responsibility, something along these lines, right? Actually, the one who's providing the compute now needs to check what it's being used for. And this is just like, in my opinion, like a really interesting and important development, right? We've seen it over time where people are just like, oh, Facebook, it's just a software, it's just a platform. There's like nothing wrong with it. But like the more we move over, I was like, well, actually, turns out we should really think about this. It's more than just a platform. You're actually responsible what happens to our society because of this. I think now the next move is something along it's like, well, it turns out you're giving this literally just this compute, which can be used for many, many good things and for many, many bad things to somebody. You should bear responsibility on this, right? And just like really think deeply what they're going to be doing it. And like cloud providers are probably the next ones. Maybe like one example of this is when AWS decided to shut down Parler, right? Which was like this Trump Facebook. They decided like, oh, actually, no, we're not doing this. This is not our type of platform. We're shutting it down. And this is an example where like somebody's providing compute and deciding like, well, actually, this is not what we want to provide or compute for. And like, I'm pretty excited about like this general note, just like, yep, compute means responsibility. This is just the case. This is the world in which you live in right now. You should bear the responsibility. You should think about it and actually implement, policies to make sure.
So what are the other examples we have of besides Parler of that happening? Does AWS have a content advisory board or something that tells them they do?
They like Silk Road. I don't know. Like you're not running your drug platform on AWS, right? That's just the case. Like I'm in Switzerland. They have like a bunch of data centers here in the bunker, and they just say like, lots of privacy. Well, it turns out they're running lots of Tor and dark web and big like illegal drug platforms, those kinds of things. If you think about illegal websites, AWS, Microsoft Azure are not hosting them, and they're checking on this, right? If you like actually violate their platforms. And I think just like, drug markets are not the extreme example of this, but it's just like one example where just like people are not excited about like, nope, I don't want to affiliate with them, right? But technically, you're just giving them flops, That's all what I'm doing. I'm just giving them flops and some gigabytes. Turns out this flops and gigabytes is running, some shady platform eventually. So you might see something around where just like, if we look at Stable Diffusion, right? No Stable Diffusion in the future might be misused for creating nudes or like deepfakes, right? We've seen this with like where like images of people have been misused to create revenge porn or something along these lines. I would expect that AWS and others are not excited about hosting these. And I think they should not be hosting these, right? So those people should actually just not allowed to deploy those models. And this is just an example of where somebody uses machine learning models. You need to deploy them on a web server to run them at scale and efficiently, right? But it's actually usage which you're not excited about. And this example is just like, we use Stable Diffusion to create like lots of nudes or deep nudes and deep fake videos, those kinds of stuff. Maybe there's an example where like AWS and Microsoft Azure in the future might be saying like, nope, this is against our content policy, which I would encourage them to do so.
It's interesting because historically, it's not really like the internet's been around for that long, but like, the lower down the stack you go, the less folks have been stressed out about these sorts of things. And, compute has been so far down, or like, NVIDIA has, had absolutely like not thought about this sort of thing at all. And sort of the higher up you go and the closer you get to sort of interfacing with people, the more the sort of like content policy stuff gets into comes into play. So for like the recent history of the internet, this has been the job of of consumer facing platforms like Facebook, Google, and Twitter to sort of draw the line, and going down to like the Cloudflares and AWSs of the world, they for a long time have been able to sort of be like, look, like this is like basically the problem of everyone else, and we're not going to stress out about it. Though increasingly, and I think like maybe like the Trump era was a bit of a turning point for this, sort of down stack became, started to draw circles which were smaller than what, a Facebook or Twitter would be. But I remember like Cloudflare at one point was like, we're going to stop hosting like neo-Nazi, like KKK stuff. But okay, once you do that, it's like, there's lots of other bad things, and like you have to rate things on the scale of bad. So, maybe like, I don't know where NVIDIA is going to draw the line. Is it going to be like, nuclear bomb modeling? Are they just going to do WMDs for what they're not cool with? I'd be surprised, frankly, if they, figured out a way to like stop people from doing revenge porn, from a chip perspective.
It's going to be hard, right? But there's been like a case of where it's not impossible. So I think like firstly there's like this notion of like the higher on the stack you are, the easier it's just like, right? The more you can blame them, whoever. Like if I'm just talking about this model, well, should I blame the cloud provider? No, I should actually blame the person who created this model, but I just can't. And I'm having a hard time enforcing this. The reason why we moved down further the stack is because of enforcement. Yep. This like actually like, or like it's the only responsible actor along the chain. Turns out the only responsible actor along the chain is like the cloud computing provider, right? And this is like an interesting notion. I think this is like in general my argument for compute. If we just talked about the fusion of algorithms and data, it's hard to enforce these types of stuff. But actually compute, we can enforce this, right? If you look at the current export controls, is there a desire to stop selling chips? No, that's not the fundamental goal. The fundamental goal is to make certain types of computationing not happening. So actually, if we could sell them chips which just cross off all of the lists which we don't want them to do, like as you just described, nuclear weapon modeling, this is what we would go for, because NVIDIA still could get their money, they're happy, whatever, all the good benefits of compute, but they don't do the nasty stuff. And maybe this is the world we're going to be moving in. And one example where we've seen this happening, and not because of social responsibility, is NVIDIA had a limiter on their GPUs for Ethereum mining. So they were just saying, like, if you buy our GPUs, we don't want you to use them for Ethereum mining, even though they've been the best for Ethereum mining, just like the best type of GPU you can buy.
Didn't people figure out how to hack that, though?
Yeah, they eventually figured out how to hack it. But like, it's also like somewhat NVIDIA to blame, right? I mean, NVIDIA got hacked. This played a role into this. And there was another page where they just like released the driver which disabled it, and then people figured it out how it actually works. But I think there's like an interesting example where you're just like, you're allowed to use our stuff, but actually you're only allowed to use it for stuff which we are excited about. And I'm in general like, I'm not saying it's a solution, but maybe should explore this more. And it's going to be hard, right? The technical solution is like, what is a dangerous ML model? What is a good ML model? We don't know. We have like a hard time telling.
Yeah, this is why it was a very funny story, because I remember like the GPU market for like gaming PCs was just like 10x what it was, and they were like, this was their PR, is that they were like trying to like throw the gamers a bone or whatever. But it
might actually be true.
Yeah, but it's
right. Well, don't you think so?
I mean, yes and no. I don't know. There was some debate. But more importantly, the idea of like the actual feasibility of putting dead man switches on AI hardware. If all it takes is hacking NVIDIA, then NVIDIA is going to get hacked again, and like people are going to figure out how to use the really expensive hardware they bought to its maximum potential. Particularly if it's a state actor who wants to use it for some nefarious purpose. So I think all of us have reached the our knowledge limits when talking about just how feasible dead man switches on AI chips in 2026 are going to be. But it's a really important and interesting question, because Leonard, you're totally right in that would actually kind of be the best thing for everyone. Is you'd keep the Western firms getting money, you'd keep China dependent on U.S. tech, and you'd just be able to sort of decide, you guys aren't going to go there, but like everything else is cool. It would be nice if that came out of some DARPA lab in a way, which
it might be in the interesting of all actors, right? Where you just basically you want to provide assurances, where they're just like, hey, you know what? Like, okay, we would like to get your GPUs, but we're not going to be using them for military purposes, and we can prove it. That's what we do. That's the reason why we do like nuclear verification and why we do inspection. It's like, hey, you know what? We would like to build a nuclear power plant, but not an atomic bomb. And it was like, cool, yeah, can we just come by like every half a year and just like check how it's going? Like maybe we want the same here, right? But that's just like the technical problem of just running flops, running operations. It's hard to tell. Is this like a good operation? Is this a bad? It's just math eventually, right? How you use it, it's going to be like really hard to tell. But I'm excited about just like people exploring this further. I guess there are like some mechanisms around it. And there might be some high level mechanisms which are something around like, well, at least it looks like you're not training a model which is that big. Like you could be making an argument just like, oh, you're fine training like models which are like GPT-3, but we don't want you to train GPT-5. And it's like one way how I could like just check it. It's just like, yeah, it turns out your GPUs have been running for the last 5 months on one big training run. We're actually not excited about this. And I think this is like technical, maybe within the realm of the possibilities, which should be explored.
I guess the challenge is that what we're talking about is actually making a general purpose technology, not general purpose.
Yeah.
And so in some ways these are so powerful because they're general purpose.
It's not the first time, right?
That makes it. What's the right example? What's the kind of right historical example?
I mean, nuclear power, right? I mean, that got sort of regulated out of existence.
I think, yeah, another way of thinking about it's like with nuclear power is just like, we're sometimes fine with uranium, but only enrich it to a certain level. Don't enrich it to nuclear bomb level, only enrich it to the level where you can use it for nuclear power plants. And I might make the same analogy just like here for GPUs. I'm just like, train your models, your machine learning models up to this degree, up to this size or something, up to this capability, but not further, because further we're like worried about misuse, misalignment, and all of those things you might be worried about with machine learning models. The analogy doesn't hold 100%, but I think it's like pointing towards something, which is just a challenge. It's something to figure out and to research, right? We should not give up, I guess.
One question I put out was, are there, when we think about computing paradigms and algorithmic efficiency, are there any ideas that sound crazy today, but might be viable in 10 years' time that you think are interesting for us to think about that could really change the way the dynamics we've discussed work?
Yeah. Yeah, saying something about the future of computing is always fun, right? maybe it's just like the base rate I'm claiming Moore's law is going to continue and be true. It's like, it's kind of fun in my engineering degree. It's become like somewhat of a norm that every professor, it's like within the first 10 sentences, they say what they think about Moore's law, if it's true, broken or not. It's become like somewhat of this meme in engineering, what they believe. And depending on which field they're in, they believe it or they don't believe it. Yeah, future computing paradigms. I'm like pretty excited about just like building on top of the existing semiconductor supply chain, like continue innovating there, right? This can be innovation on like the transistor level, right? Basically, just look at the roadmaps of TSMC and ASML. But other stuff like in-memory computing is probably pretty interesting for machine learning stuff. 3D stacking of chips is interesting. And I think this whole general notion of just like building bigger computer clusters, just like how can we be doing distributed computing better? Turns out we need a lot of chips. There's a limit to how much our single chip can perform. So we just like distribute them, like build big clusters. Or maybe also companies like Cerebras, which is like trying to build like a wafer scale chip. I think it's like also pretty exciting and interesting technology. And this, maybe this is in 5 years from now, maybe 10 years from now. I mean, they probably have like better timelines than this. I think those are like in general like interesting ideas. What I'm eventually like interested in is maybe not the single performance of a chip. What I'm eventually interested in is like the price performance. So like maybe another idea is just like we currently have like those really short R&D cycles, right? And as we just discussed, you need to spend exponentially more to get like your transistor exponentially smaller, or like get your computing performance. Like this might hit limits. And if we stop have like those really short R&D cycles, if like instead of your iPhone coming out every year, it comes out every 3 years, you might actually have like better economies of scale. So like while the performance per chip stays the same, you can make the chip smaller, like cheaper. So it turns out you basically have like better price performance. And like if we go back to just like how much we want to spend on training a model, this is eventually the thing you then care about. And this is maybe something worth exploring. I like never really looked into this, but I would just expect instead of like the current crazy R&D we need to do every single year to continue innovating. If this becomes longer and you spend less money, we might just scale up facilities, we might just come up with more users, or we have like a stronger pressure on algorithmic efficiency and like new paradigms. But there's like nothing which I'm betting on. Like if I learned one thing about technology, it's like, yeah, there are like some things which I'm more or less excited about, but it's like not the one thing which is going to solve it all, or something which like needs to be figured out, I guess.
Final question that sparked back to the China export controls debate. How would you assess this argument? Well, China can't access the most advanced GPUs, but it can just build very inefficient data centers using less advanced GPUs.
Yeah, I think it's a thing you actually should be thinking about. And I'm currently trying to look into this. I'm just like, can you just use like a GPU which is half as good, but you use 2 times as much? Is it just like, naively you could say it's like the same performance, right? But it's like this thing of like sublinear scaling, the more GPUs you use. So it's just like, it's the same when you work in a team. Do you rather hire 2 half-time people or 1 full-time person? Most people go for 1 full-time version because there's a limit in coordination. Turns out we humans are pretty bad at this. Computers are a bit better at this, but they're not perfect at this. So you don't have linear scaling. And I guess that's probably the thing you want to look into, right? It's just like, turns out we need lots of communication with those GPUs. The performance doesn't scale linearly with like the amount you have. So like, you cannot just use double the GPUs. And the other problems you're having, if our current progress in hardware continues, again, exponential growth, you need to exponentially grow the number of chips, right? And I'd be surprised if you put, 1 million chips in one data center right now and just like make them all work together.
Well, if you solve the sort of communications problem that you discussed and got that to scale linearly, then it seems like, Moore's law over, which would be better. And, at the rate of Moore's law over the next 5 years, you could brute force your way around the problem over a 10-year time horizon.
Yeah. I mean, the thing is just like, it's easier for TSMC to produce like double as much chips than just like continuing making the transistor smaller, right? So if we could just solve the communication problem, sure. Yeah, it just turns out it's like actually really, really hard. I think the thing which I'm more interested in is more about, it turns out that our ML, machine learning algorithms, need a lot of communication. What if we have like new algorithms which don't need this, right? Which are just like less communication heavy. And those are the things to look out for, right? There's like a couple of folks who are currently trying to like develop new algorithms to train systems decentralized, right? So like instead of using 1 data center, we use like 5 data centers spread around. And I think this is something we should look out for. What are the algorithmic innovations along these lines? And this then actually informs it, right? It's a thing. Like, well, let's see if we're going to be seeing this happening and what are the scalings to how many chips we can put in one place. I don't know yet, but it's definitely on my radar.
Well, this was a treat. For folks looking to learn more, I would recommend starting with SafeCon's AI Chips Primer, which was published in January 2020 at CSET, and then running through Leonard's syllabus, which hopefully by the time we publish this will be available for the world to explore. Leonard, you got a song for us?
Gosh, there's nothing from the top of my head. I would be keen on you playing like another fun Chinese song. This has always been a treat when I listen to the podcast. So yeah, you pick Jordan.
iPhone 做这个 beat， Black Dog 播的 Follow Me， Project 2年度专辑你知道，约在北京。020的2变成1，不能接受第2，除非2变成1。我知道你们平常喜欢直接进 rap， 但这么好的 beat 再呼吸一下不急。妈，因为 human 的 flow 那么万神殿给翘起，指挥广东兄弟们力争上行，知道我的标准比牙签更挑剔。背着上台，我能看到我的对手脸色变得全白 C major， 或者变成 A minor liner， 下手干脆的 rhyme 就这样变化，是弄乱的发型 ，mistake 杀进 mistake 发现南面的 top 的 top， 在广州却感受到高海拔气压，无视那片面的垃圾话。我坐摩托坐着阿基拉，真理的味道是哈密瓜，这场面炸得像萨琪玛。祝你身处人遍布的岁月，那真理可森，准备疯人院的飞跃，把英雄本色洒入的画布的颜料流出了友情岁月，还是还有烈，是想对我威胁自己，把自己给崩了，像那大逃杀的背后，每天做的梦都是一部 sci-fi 三体，应该邀请校长来做配乐 ，hip hop 的莫里康，锅里烫着 B， 再做几张专辑，总计我的货币量能在北京买个房贷落地窗。以前看我哥们筹备学 G-Funk， 现在看我哥们筹备学区房，就算不再年轻，但态度没变，还穿的是合体的街区晃，坐着敞篷车，打开天窗说亮话，说唱是无形资产，他们没有办法来把我给量化，在这社会上混，哥们不仅得知道那标准答案，还得抢答，真的满身都是汗，有时感觉冠军戒指像桑拿。当我踏入赛场，上一秒舞台上， 下一秒屠宰场，是谁杀死的比赛？福尔摩斯说只有 AR 没有不在场。And you know I'm the go right， like 悠哉，其他的 rapper 可以开始争夺榜眼，探花镜是巨人和秀才 ，skill 是练就云南 live house， 所以说向往是个技术宅。合约的要求像到店自取，得靠你自己提出来，灵感都多得快溢出来，演出造型让我的溢出来。这世上有人斗起饺子嫉妒爱，他们黑 AR 却离不开。我的曲风有点吉普赛，现在给不到你，未来才能明白。所以未来的你都想踩到信条，回到现在告诉你喷啊太不应该。给超市的嘴里塞几斤测着收手机编曲不够的懂歌都应该重新高考英语，因为他们需要听力测试，不会辨别什么叫做好的音色，太多青涩的评测，形形色色，没时间理，哥们忙着研究汉语，说唱的平平仄仄，装上没主见的听众被带跑，太多节操都变成了碎片的圈子，不仅变得脏，它变得比脏变更加内卷。最近北极天气像阿根廷沙特一样爆冷，我得做点热菜，看对手什么角度，广东娃公全部都爱调侃，煮币煮到我的手腕烫，点个碱水面配肉丸汤，他只赶上互联网战场我爱吃，但我从不跟黑粉在豆瓣酱。我明白了无敌最寂寞，所以做了一首歌叫 Lonely。常去的银行在瑞士，但如果兄弟有 beef， 校长绝不会中立。刚暂停的打击乐重新鼓起，像勇气。你跟我比腔调，像我跟杨和苏比胸肌。Am I even human 的 flow 那么万神殿给跳起，指挥广东兄弟们力争上，想知道我的标准比牙签和挑剔。别上台我能看到我的对手脸色变得全白 C major， 或者变成 A minor liner， 下手干脆的 rhyme 就这样变化，是弄乱的发现 mistake 杀进 mistake 发现南美的 top 的 top， 在广州却感受到高海拔气压，风吹而且爱已经做到了极致，台下的观众者 head 抬头，当我带领我的兄弟们联合开收，如果螳螂捕蝉，广东 stand up 在后。